So, very briefly, if you're leaving today or if you're leaving tomorrow, you can leave your luggage with Alicia and Megan next door, right? So if you bring your luggage from the hotel, you can leave it with them. In case you weren't able to find a good lunch option yesterday, do let the locals know, and we will be happy to do some feedback. And then one last thing, I think I mentioned yesterday, just as a reminder, Anja Botana was unable to come to the workshop, and in her stead, Fiona Burnell agreed kindly to fill in after Steve.
Great, thank you. So, good morning, that's Daniel. So we have now the absolutely definitive hard-hitting word energy.
When do I?
It was 25 plus 10. Or 30 plus 5.
Okay.
Yeah.
Right. Let me just put your side. Sorry.
Okay, so despite the muted titles, I'm very excited about this work. I think it's the first really direct evidence of air density wave. It's the first clear prediction that can be confirmed as opposed to sort of explanations and post-its. So, the work appears in this paper, and this is basically an experimental talk. There'll be very little theory. This is meaningful work. So I see it as off. This is physics of the cuprates. There's a lot, all the papers that try to get published in fancy places start with, here it's 35 years after the cuprates were discovered, and we still don't know anything. And that's completely wrong. We've really understood a lot. We understood and everything about apparent insulating phase. It's not described by spin wave theory. We know that the superconducting state is E wave, that the low energy physics is completely captured by BCS theory and E wave superconductor. The superfluid density is small, and that this is unrelated to BEC to BCS crossover. And that it has this extremely complicated phase diagram where multiple different forms of ordered phases are, for some reason, which is not completely clear, are tied up with each other and you simply can't get rid of them. So that's a lot. Here's a phase diagram that appeared in a paper that was a triumph of diplomacy, nothing else. So the question I want to ask today is about whether in this phase diagram there is any role at all played by the pair density wave order. And I'm under the impression that now pair density waves are being seen, or at least claimed to be seen, under every bush. I was trying to document that. So I looked up in Web of Science under pair density wave hyphenated and found 3,375 articles, sounds like a lot, then says that of those 3,113 without self-citation, but I don't know how a pair density wave can self-cite it. So I decide I don't know what these statistics mean at all. Okay, anyway, put that aside. So the first question I want to ask today is do we really have evidence that there's pair density wave anywhere in the phase diagram? There is a still stronger statement that's been made by a number of reading lights in our field, but not only does the pair density wave exist in the phase diagram, but it's the central drama of the phase diagram. It's the mother of all orders and the source of the pseudo gap. And in case I get rushed by the end, let me tell you what my answers to these questions are. The answer is this is extremely unlikely, but this is reasonably well, I hope to convince you that pair density waves do exist somewhere in this phase diagram.
Right.
Okay, so let me define pair density wave for you. So we look at the superconducting order parameter. It's a 2-point function. So big R is the center of mass coordinate of the Cooper pair, and little r is the relative coordinate of the Cooper pair. Unconventional superconductors are ones in which the average over the relative coordinate of the pair field order parameter is 0. And pair density wave orders are ones in which the average over the center of mass coordinate of the pair field is equal to 0. The most famous example of a pair density wave is the so-called FFLO states. That's actually 2 different states, but both of them satisfy my definition of a pair density wave. So those are, in fact, a pair density wave. The pair density waves that I'll be discussing are quite distinct from FFLO states, both in their microscopic character, that is to say, the mechanism that gives rise to them. We don't understand the mechanism that gives rise to them, but we know it's not this. And in terms of, if you carefully specify what are the broken symmetries, the set of broken symmetries are somewhat different. So there's a precise sense in which they're different. From a statistical mechanics point of view, a pair density wave is to a uniform superconductor as a spin density wave is to a ferromagnet. It's the same sort of local ordering, but with rather different, importantly different spatial structure, which means the macroscopic properties can be very different.
How is it different from FLLO state?
Well, so for instance, an FFLO state has net magnetization, so it breaks time reversal symmetry. And time reversal times any translations, whereas the pair density waves that we're interested in don't. And that's a very fundamental aspect, because for the FFLO state, the ordering vector is proportional to the magnetization, whereas here there's no magnetization and the ordering direct vector is determined by some strong correlation. Okay, so I'm going to be doing order parameter theory. So I'm going to be thinking about an order parameter. It's going to have a uniform piece, which I'll call delta naught, and it will have a pair density wave piece, which for simplicity, I'll have only at 2 momenta, although this can be easily generalized, momentum Q and momentum minus Q. So these are the amplitudes of the different components of the superconducting order. There will also be charge density wave order that's playing a role in what follows, and that is going to be represented by some amplitude phi sub k. But it's also possible to get charge density wave order as harmonics of other orders. And in particular, if I have superconducting order, then if I have pure pair density wave, then I can generate a charge density wave order as a second harmonic of the pair density wave order. And if I have coexisting uniform superconductivity and pair density wave order, then we'll get a harmonic at momentum 1q. So these induced charge density wave orders are the things we're going to be looking for in experiment. This is this is the central actor in the experiments that I'm going to describe.
A simple question. Why is it important to have opposite spins in that correlator? Is there a chance to pair parallel
Yeah, you
spins
can have a triplet pair density wave.
SDW as a second harmonic?
Exactly.
Uh-huh.
I'm, for the cuprates, everything is in the singlet channel, so I'm focusing on that. You know, you could also have opposite, you know, the spin one version of this. So, but anyway, I'm just, to keep things simple, I'm looking at singlet. There's no particular reason not to consider others. There's some interesting data on one of the iron-based superconductors by Pasupathy that probably has to do with triplet pair density. So even.
So a quick question, is it possible, I think it is possible to have the opposite, where you have a CDW and it imposes a modulation on the superconductor?
Absolutely.
Yeah.
Yeah, so the relation will be different though. Sorry, if you have uniform superconductivity and a charge density wave, that would induce pair density wave at momentum q. But a charge density wave by itself doesn't induce superconductivity at all. So it's if you have coexisting uniform and charge density wave order, you necessarily generate then pair density wave order. That would be considered a parasitic order. I wouldn't consider that separate. And many, maybe most of the claims of observing pair density wave order, I would say, are just parasitic order produced by coexistence of uniform and charge density wave order. Yes?
In writing this coupling term, delta naught and delta Q, you assume probably that both uniform and delta Q components of superconductor parameter have the same phase.
No.
They are not independent on each other.
So there'll be terms in the free energy that will lock their phase. There'll be terms like delta naught star squared, delta Q, delta minus Q, which will lock their phase modulo pi. Those are inevitable if they coexist.
I think maybe one of is saying that you could construct another one with the imaginary part, then wouldn't be a CDW.
Oh,
right?
that would be a current density.
Yeah.
wave. Yes, indeed, you could get a current density wave. The way I've written it here, the charge density wave ordering vector and the pair density wave ordering vector are separate. Typically, if they're close to each other, then there will be energetic preferences for commensurate locking. And I'm going to always imagine that there is such locking that plays a role, just again, to simplify my discussion. Okay, and so the interesting thing here is coexisting uniform and pair density wave always lead this 1Q order, which is then a subharmonic of the dominant 2Q charge density wave order. And so that is something that's notable. Okay, so there really isn't an acceptable microscopic theory of pair density wave formation. There's a very generic understanding of how uniform superconductivity occurs by a BCS mechanism. There's a very generic understanding of how unconventional superconductivity can arise from repulsive interactions. There's really, there are now a few sort of engineered models where we can find pair density wave in a convincing way. So things are better than they were. But if you ask me what are the physically important ingredients to drive a system into a pair density wave state, the honest answer is it's got to be a system that we understand poorly enough that it could happen because we don't know why it shouldn't happen. However, there really is now strong phenomenological evidence for its existence. So despite the lack of compelling theory, I'm going to go on and explore it. if there's no theoretical reason why pure density wave should be forbidden. It's a perfectly legitimate form of symmetry breaking. Here's another triumph of diplomacy, a review up to this point of what was known about pure density waves and a number of things that weren't known. So what I'm going to talk about is new since this was written, and it's evidence of the existence of this predicted 1QP. All right, so I'm going to look in one particular family of high temperature superconductors, the ones with the LTT structure. Here's lanthanum, barium, copper oxide. And lest you think that I'm picking a particularly weird outlier, this is the most important cuprate because it was the first cuprate that was discovered to be a high temperature superconductor. It also has this very spectacular phase diagram with a very pronounced so-called 1/8 anomaly where the superconducting TC drops to a very low value. It has particularly strong charge and spin density wave order. And I'm going to focus on samples near doping 1/8. And I'm going to tell you a little bit more about the phase diagram of this. So here's as we come down in temperature in lanthanum, barium, copper oxide, 1/8 doping. On this slide, you can see there's a structural phase transition from a low temperature orthorhombic phase to a low temperature tetragonal phase. At around the same temperature, there's an onset of charge density wave order. At a slightly lower temperature, there's an onset of commensurate spin density wave order with twice the period as the charge density wave order. But what you see here are the electronic responses of the system. So in green is the in-plane resistivity, which does something a little bit at this charge ordering temperature, but then plummets by an order of magnitude at the spin density wave ordering temperature. So it becomes almost superconducting in plane. At the same time, the interplane tunneling resistivity is growing and continues to grow as the in-plane resistivity goes roughly superconducting. What's shown here is the magnetic susceptibility with the magnetic field either perpendicular to the planes. So here you see the superconducting transition as signaled by the Meister effect at this low temperature down here with the resistivity, sorry, this is with the resistivity in plane. With the resistivity perpendicular to the planes, you see that there's substantial diamagnetic, what?
Susceptibility.
Susceptibility.
You said resistivity.
Oh, susceptibility. You see that you get substantial fluctuation diamagnetism even well above TC, but again, you get the superconducting transition here. Just to blow this up, these are the same data now, not on a linear plot, but on a logarithmic plot. And what you see is this in-plane resistivity continues to plummet and extrapolates to 0 at some temperature here. They've even fit this to Kosterlitz-Thallis in order to extract a Kosterlitz-Thallis transition temperature. That's why this is called TBKT. At this point, the resistivity in the C direction is still very large. So this is, at least on the face of it, a spectacularly impossible state of matter, which is superconducting in 2 directions and resistive in the third. I was worried for many years that this might be some nasty way this material was lying to us, but in the meantime, very, very similar transport and susceptibility data has now been seen in a host of related but distinct crystals by a large number of different groups. So I think that this sort of behavior, spectacular as it is a fact. Okay, so I want to comment on how strange this layer decoupling is. And so I'm going to talk by analogy with ordering of a ferromagnet, but you should think of the ferromagnet being a proxy for uniform superconductivity. And the thing is that if I had a quasi-2D ferromagnet with interactions between the magnetization and neighboring planes, then as you approach TC from above, the interplane coupling gets amplified by a factor of the coherence area in each plane. And so even if you start with a very anisotropic problem, as you approach TC, it becomes more and more isotropic, not more and more anisotropic. So this effective anisotropy goes down the more closely you are to being ordered. And you end up with a transition temperature that's a finite amount above the predicted TKT. In an antiferromagnet, this interplane coupling can, under some circumstances, be frustrated. So that's actually, here's a picture where we have antiferromagnets on two different planes, but here you can see that the spins on this plane are above the plaquette center of that plane. So the coupling between planes is frustrated, and therefore the J effective is 0. Now, that's not actually quite true. You generate higher order couplings. You get something like order from disorder, which generates some couplings between the square of the Néel order parameter on neighboring planes. But this is much smaller than the bare anisotropy. So from frustration, you can get a major amplification of the anisotropy. And this is presumably why in lanthanum cuprate, you see two-dimensional antiferromagnetism down to temperatures in which the correlation length is maybe several hundred lattice constants. Yes?
And to be clear, unlike the other one, this effective coupling does not grow as you approach a transition.
Well, it does. This one grows also, but it starts to be, if J perp over J parallel is 10 to the minus 3, this thing is 10 to the minus 6. So it has a much longer way to grow.
But those are the local, is N just a single
local.
plaquette or?
No, it's the local spin.
Okay, so it doesn't have this divergence with the.
It does. So as the spin correlations get bigger and bigger, this gets amplified. So still, there's no escape from it. Once a thing really orders, it orders in 3 dimensions. You just can't escape that. But what this means is that you need that much bigger growth of correlations before they lock. And so, in fact, that's what happens for the spin and charge density wave order in the cuprates. You see very long but finite in-plane correlations and almost no interplane correlations because the couplings between planes are frustrated. Okay, so we propose that that's what's going on here, that we have pair density waves on neighboring planes. For various structural reasons, we expect them to be oriented like this. And so the leading order Josephson coupling between neighboring planes vanishes by symmetry, just as it would in an antiferromagnet. And that's what we claim allowed the superconducting correlation length to grow extremely large in plane while not producing any 3-dimensional signatures. Okay, so that's great. If pair density waves were ubiquitous, I wouldn't have to be telling you about this one strange family of cuprates. I could be telling you about any family of cuprate. And in particular, we could look for this 1Q peak if we had pair density waves everywhere, but we also know we some places have uniform superconductivity. We should see 1Q peaks there. And they've been looked for. They've been looked for in particular in YBCO. Here, here's the charge density wave having its own intrinsic piece, maybe a piece produced by as a harmonic of a spin density wave and as a pair density wave. That's just to remind you. But then if there's both uniform and pair density wave order, we should also see a 1Q peak. And here is some data. You know, it's hard to get people to publish negative data. I've been trying to get people to publish. There's lots of data like this. This is probably the best, but this is YBCO. As they change the magnetic field, they enhance the charge density wave order at 16 Tesla. They see long range 3-dimensional charge density wave order. However, it's still superconducting, so it presumably has a uniform superconducting component. Here's the magnetic field dependence of the structure. Here's the charge density wave peak, the 2Q peak if you want. There's the 1Q peak, it's just gone. This is at L equals 0.5 in the C direction. Here's at L equals 1. This is some new, stronger 3-dimensional charge density wave order coming up. But again, nothing shows up at 1Q. Okay, it really doesn't exist there. Now, negative evidence is always hard. You always prefer positive evidence. Okay, so I want to look in this material where, for other reasons, we think there's pair density wave, and to see whether we can find the predicted 1Q peak there. So I would like to look in some region where I think that superconductivity and pair density wave coexist, which means I want to be well below where the layer decoupling occurs, but as close as possible to where the Meissner signal turns on.
You have 10 minutes,
10 minutes, okay, good.
including questions.
Okay, I'll try to finish in 5 minutes. So here's the phase diagram that we've just discussed. And so what I want to do is report to you resonant soft X-ray scattering on 2 of the materials that show this phase diagram. One is iron doped LSCO, and the other is strontium doped LBCO. So the good news about resonant soft X-ray scattering is that it's directly sensitive to electron density wave order. You don't have to look for charge density wave order by motions of ions. And this was actually the method that was used to discover charge density wave order in YBCO. So here's the data on the iron doped LSCO. What's going on? I thought, yeah, bad news. I wanted to tell you the bad news. The bad news is that there's a well-known feature of resonant soft X-ray scattering, that there is a large background signal from, from spectral scattering from the surface and fluorescence. And so here you can see that even at the primary charge density wave ordering peak, which is a very strong peak, there's not much going on. In order to look at this, we use the fact that this background is believed to be temperature independent. And so what we're going to do is we're going to take the signal at high temperature, which we think is mostly background, and subtract it from the signal at low temperature, which should leave the signal. Okay, and this is the standard method that's used for resonant X-ray, soft X-ray scattering. It's the fact that we had to do this which was responsible for the somewhat muted version of my title. I don't like subtraction, but it is standard. So it is. So here's the subtracted data. So here's here is the 1Q peak. And so here I take high temperature data, which is 60 Kelvin, and subtract it from the data below the onset of charge density wave order. And indeed, you see the 1Q peak is really a very prominent peak. And then if I go down as low as they can, 25 Kelvin is their base temperature in this experiment. So as close as possible to the Meissner state. And now you see this 1Q peak appearing just where it's supposed to. If you look off resonance, so you're not expecting the signal, you want to check how well this attraction works. That's what you see here. There's just no signal at all. Let's see. These traces implicitly also take you in a trajectory through L. Here is along a trajectory that goes through where you expect to see the charge density wave. Here's a trajectory that doesn't. All right, so I've run out of time. What I want to say is we have seen the predicted 1Q peak where it should be. That also means that the negative results in YBCO should be taken more seriously, and therefore the pair density wave as the mother of the charge density wave state has been falsified. Okay. I've said that. Is it important? Well, look, it's a new phase of matter, so I think it's important. It has no plausible origin in weak coupling, so that's interesting. It's perhaps the most vivid example of this role of intertwined order in the cuprates. And I wanted to warn you that probably the actual materials are inhomogeneous messes. So if you try to really understand what this means, it's probably going to be pretty complicated. And with that, I'll stop.
So questions, start at the back.
Clarifying question. The way how you presented it, pair density wave has nothing to do with charge density wave. It's independent order, right? Nevertheless, in experiment, it shows up when charge density wave is there. And is it a warning sign, or that maybe it's still induced by a combination of superconducting fluctuations and charge density wave?
So I think the answer is yes and no. So first place, I think the really serious thing is it occurs where we have spin density waves. And I think the basic observation is that my enemy's enemy is my friend. So I think the pair density wave is almost always killed by uniform superconductivity. Uniform superconductivity is the big bruiser. Spin density wave order is, of course, very antithetical to uniform superconductivity. The pair density wave can interleave through the spin density wave order, so it's much less suppressed by spin density wave order. And so, in effect, it's enhanced by the presence of spin density wave order. So that's my, my microscopic intuition about how these things, and of course, the charge density wave order is part of the spin density wave order. So indeed, there is a correlation with the charge density wave order.
But in one phrase, you believe that pair density wave can exist independent on any charge or spin density wave.
It can, it just usually loses to uniform superconductivity.
Right.
Yeah, so if you can figure out a way of getting rid of uniform superconductivity, pair density wave as a subleading order should be all over the place. Why not?
Steve, I wanted to ask about all these other observations of PDW, not all of them, but as you mentioned, right, more and more reports, especially using the Bogoliubov QPI.
Yeah.
And in a lot of these materials, there's no CDW, right?
Right.
Like uranium, telluride, iron. So what is your take? I mean, you mentioned something, you believe that most of these are parasitic orders, but I just want to know your feeling. Is PDW really showing up in all of these, or are we being?
No, I mean, I think it's pretty safe to say that most of the places that PDWs have been seen, they're either being misreported, they're just parasitic orders, or that there's probably some other interpretation of the experiment. Some subset of them may well turn out to be right. Now that I'm convinced that we've established it in one place, I'm more positive about it in other
I'm
places.
gonna try and get a few more questions. There.
Independent of your thoughts about the validity of the experiment, isn't it a fact that this Q peak was seen in STM? In vortex cores?
So this is exactly the same peak that was seen in vortex cores in Bisco.
Yeah.
Indeed.
Yeah.
And that, by the way, I think is the only reason that experiment doesn't have me quite as excited is that it's not a bulk experiment. This is the first bulk experiment, but
Very simple.
that was actually another case. Consider a multi-band system, you know how it starts.
It's really very simple. I'm just trying to understand it better by this analogy with full differential, which you dismissed on the ground of uniform magnetization. But magnetization is something that creates spin splitting, and we know that spin splitting can exist without magnetization. So let's say this is spin up, this is spin down. You can have perfectly well full differential state like this. How is that different from your predicate? It looks like condensate looks.
No, that would be fine. That's a very different mechanism. It's a.
But it is the same thing, right?
No, it's not. No, because full differential or like the Chenikov state is a state that appears as instability of uniform superconducting order.
But
Your
that-
order
that-
is not,
that-
does not
that-
I
appear.
think this is gonna be.
Yeah, no, that's the reason how it appears, but at the end of the day, it's the same, right?
And I'm gonna bring up at some point later serial covalent. But
This should be quick. Just could you remind me, the system that you talked about at the end had iron doped into the copper?
Yeah.
So to what extent is it still a superconductor at all?
So it's still, so that's an interesting material. So it still has the LTO structure,
Right.
but it's a small amount of iron which stabilizes the spin density wave. So that's actually part of the response to Andre's question. So it's still a superconductor. It's low iron concentration, but what the role of the iron is that it enhances the spin density wave order and thereby seems to also enhance the pair density wave.
So I think we should probably move on. Fiona.
Yeah, it's fine. You want these all?
It's this light bothering you?
Yeah.
So I think if you can find maybe.
No.
Yeah, this is good. This is good.
I mean, it was okay, right?
It is good right now.
It's just another symmetry, yes, nobody's.
So it's just. I will tell you at 25.
Okay, so as Martin mentioned, I'm filling in for someone, so I'm gonna tell you about something a little bit different probably than what's in the rest of the workshop. And this is work that was done, kind of initiated when I was on sabbatical at the IIT in Princeton with two very good junior colleagues, Abhinav Prem, who's still a postdoc at the IIT, and Sanjay Mudalia, who's currently postdoc in Dresden. Okay. And so the nature of the question that I'm going to ask is a very kind of big picture question, decoupled from any details of the system, right? And this is a question that probably some of you are familiar with. So I'm going to ask, under what situations does my system kind of have to do something a little bit non-trivial, okay? So the basic question is, let's suppose that I have a system, it has some kind of translation symmetry. And it also has some other symmetry. And maybe spin rotation invariance, or it has a charge conservation, okay? And it has some particular symmetry for charge per unit cell. And the question I'd like to answer is, can I always form like a really boring ground state that's gapped, short range entangled, non-degenerate, and symmetric, okay? And of course, I think you're all familiar with the fact that in general, the answer to this question is no, okay? And so here's a good example of the kind of thing you should have in mind when you think about this question. It is of course very different to have an odd number of spin-and-a-halves per unit cell than an even number of spin-and-a-halves per unit cell, okay? And why is this different? Well, first of all, let's look at the even number of spin-and-a-halves per unit cell, okay? And here again, I would like to ask, you know, can I, like, what's the most kind of uninteresting thing that I might do? And that's obviously a subjective question, but one of the things that I could do with these, you know, even number of spin-and-a-halves per unit cell is I can just pair them up, okay, into singlets. And now if I take, you know, each red spin and singlet bond it with a blue spin. And now effectively I've taken my, you know, sort of two-leg ladder of a spin-and-a-half system and turn it into a spin zero chain. This would be my ground state, right? And you can see that this ground state breaks no symmetry. So obviously spin rotation invariance is preserved, translation invariance is preserved, and you know, it's gapped, okay? So this is kind of the most trivial and boring thing you might think of. Okay. And so this is why, you know, when we think about interesting magnetic systems, we like to have an odd number of spin-and-a-halves per unit cell, right? And then you can just ask, like, what kinds of things might I be able to do with my odd number of spin-and-a-halves per unit cell? Well, I might be able to order them ferromagnetically, right? Well, this obviously breaks spin rotation invariance. Okay, fine, you maybe can't, maybe they're isospins, can't really do this. 1D, okay, but you know, maybe these are 1D chains in a bigger system, okay? Or, you know, I could imagine, again, other kinds of orders that I might have an anti-ferromagnetic order, or I might pair each spin-and-a-half up with one of its neighbors into singlet bonds, but these break translation symmetry, okay, among other things. Or if I don't want to break a symmetry, then, you know, we all know that I could also have a Ledinger liquid, but this is going to be gapless, okay? So it has long-range correlations. So the mere fact that I have an odd number of, you know, spin-and-a-half degrees of freedom per unit cells, right, kind of locks me into doing something that's at least a little bit non-trivial, okay? And so, you know, this is sort of, I think, well known, familiar to everyone when you talk about an odd number of spin-and-a-halves per unit cell. And I think we're going to hear some talks later in the day that talk about sort of frustrated magnetism related things. And of course, this is sort of one of the necessary conditions that you want to look for if you want to look for a quantum spin in dimension. Okay. Oops. I didn't write down where I stood. Okay. So this is kind of the basic idea that I want to get at in today's talk. And what I'd like to do is tell you about some, you know, kind of generalizations of this beyond symmetries that people have thought about in the past. And so the first thing I'm going to do is I'm going to review the kind of argument that I'm going to use, and I'm going to review it in the case of a system that conserves a U1 symmetry, such as an electric charge, or maybe the Z component of spin. And then I'm going to tell you how you can apply these arguments in systems with a stronger symmetry. Okay, so I'll tell you a little bit about why you might be interested and why people can essentially, you know, roughly speaking, realize experimentally systems that conserve not only something like a charge degree of freedom, but also systems that conserve dipole moment. So kind of higher multipole moment symmetry. Okay, so let me start with a kind of review of and sorry, I should say that, you know, this kind of general class of obstructions to doing something really boring. They were first, you know, introduced by Lieb-Schultz-Mattis, so they're typically referred to in the literature as Lieb-Schultz-Mattis theorems. And I'm first going to review a rather different kind of argument, a more topological argument that was introduced by Masaki Oshikawa in 2000. Okay, so so here's the scenario that I'm going to think about. I'm going to have some number n of sites on a ring, so a 1D system with periodic boundary conditions. Okay, and I'm going to have some conserved charge, right? Which obviously I can express in terms of like a number operators. This is like the number of fermions or bosons at each site. And to make life simple in this talk, we're not going to have spin. So if these are fermions, you can think of them as being spin polarized, you know, or maybe, like I said, there's some kind of bosonic degree of freedom and they never had maybe it's SC, okay, so I don't. Okay, and so this symmetry is always going to have, sorry, this system is always going to have a conserved total charge, okay, so Q hat is a conserved quantity, and with that conserved quantity, I can generate a symmetry, a U1 symmetry under global phase rotations, right, and if you want to kind of remind yourself of how this works, you know, basically effectively when I take this operator, u to the I alpha, you know, Q hat, then, you know, for the purpose of the ground state, it basically rotates each fermion creation operator by phase. Okay, good. So now I want to ask the question, you know, I want to ask this question about, well, okay, so I have some charge filling and you know, does the system care what this charge filling is in terms of its ability to do something a little bit boring? I mean, you might expect that naively the answer would be yes, okay? And one way to think about this is to ask, well, what happens? This is a system on a ring, right? It's round. We can insert a magnetic flux through the middle of the ring. And you might ask what happens when you do that. So let me quickly remind you of how this works, okay? So when I put a magnetic flux through the ring, okay, like imagine like a little solenoid in the middle of the ring, okay? So obviously when I'm turning on that magnetic field, there's an EMF and you know, these guys are going to feel electric field, something's going to happen, okay, maybe I'll put some energy into the system. But you know, maybe I do that very slowly, and I'm going to put in a very small flux, so the amount of energy change is not going to be changed, okay? But let's just sort of think about at a given moment in time. So I do this with a background, you know, what happens to the charges, I introduce a background, you know, gauge field, electromagnetic gauge field. The flux is given by the line integral of A dot dl, right? And so, you know, if my lattice constant is little a, then this gauge field is a, this is ax, okay, as little a divided by the length times whatever flux I want to put in, okay? And now you can ask, like, what are the particles in the ring feel when I insert this flux? And the answer is they feel what's called an Aharonov-Bohm phase, right? So this is something that we saw at some point in your life in quantum mechanics. And what does that mean? Well, let's suppose that, you know, I put only one charge in the system, and it's going to travel around this flux, okay? And right now the flux is static, so it's not experiencing any electric or magnetic fields. The electric and magnetic fields are all zero on the edge of this ring. But what happens is that this wave function picks up a phase. Okay, so this is, you know, effectively my flux is just modifying the boundary condition for my flux. That's all this is. Okay. So Masaki then said, and you know, this is kind of a useful exercise. So he said, okay, we have this Aharonov-Bohm phase. Let's imagine that we thread a single flux quantum. Okay, so after I do this, right, this net phase as I go around the circle is too high, and physically everything has come back to the same place. Okay, there's no net Aharonov phase. But there's a little subtlety here. Okay, so from the point of view of the electrons, they no longer see, you know, they see again, you know, if I started with maybe periodic boundary conditions, they still see periodic boundary conditions. Okay, so kind of like physically nothing has changed, but if you look at the details at this gauge field, right, here my gauge field was all zero, and here my gauge field is 2 pi over L times the lattice constant, so it's not zero. And so there's a subtle difference, okay? And Masaki's, I think, you know, crucial observation is that when you do this kind of procedure, you have to be a little bit careful, okay? So you've inserted your flux, you want to know what happened to the system, and naively you've inserted a flux 2 pi. Nothing happened to the system, it looks exactly the same, but it's a little bit subtle, okay? Because we've ended up in a different gauge, and so the right thing to do is to compare apples to apples, and we want to restore my original, you know, sort of gauge configuration. I want to put these A's on the links back to 0. And I can do that with this product of local unitary operators, okay? So I basically just do a site-dependent rotation of the phase of these fermion creation operators, okay? And this will put me back to exactly the configuration that I started. Right? So now you can ask, okay, now that we know, now that we can do this process, we come back to the same place. We're comparing apples to apples. What happens to my system over this process? Okay. And the first thing that I want to emphasize is here I'm putting in a single flux quantum. So yes, when I'm inserting it, I'm threading it, there is potentially some energy change, but that energy change is very small, okay? So basically, if I have an energy gap in my system and I make it long enough, I can always organize that, kind of energy change I can make my system big enough that that energy change is not going to be able to create excitations above the gap. Okay, so the idea here is this is a process that kind of, because the amount of magnetic flux that I'm putting through the middle is very small, is going to take a ground state to a ground state. Okay. Point number one. Point number two, okay, so now my system had translation invariance. So before I did this, it had some total momentum, okay? And, when I do this flux insertion process, I can do it in I'm just changing the Hamiltonian by adding this pH field. I do it in translation invariant way, okay? So this momentum is conserved actually over this flux insertion process. But you can ask, what about this, kind of naively, and if you work with gauge fields, that this is a bit of a slippery thing because momentum is kind of a gauge dependent quantity, okay? So you can ask, what about our gauge transformation? Does this gauge transformation change the many-body momentum? And so we can look at this operator. So this was the operator that we used to restore our original configuration of gauge fields. And you will notice that it doesn't actually, because of this J in here, it does not actually commute with the operator for lattice translations, right? But it only commutes actually up to an overall phase. Okay, and here's this overall phase. And it basically depends on the number of the ratio of the number of charges in the system to the number of lattice sites in the system. So here I've set E and H bar to 1. So if you're wondering where the constants are or what the units are, that's the units. Okay. So the consequence of this is, before I had a system that was translation invariant, it had some momentum. Let's call that momentum P naught. Okay. Now, after this gauge transformation, basically, let's ask what happens if I translate the effect of this operator acting on a state with momentum P naught, which I'm, also calling psi because they have the same momentum. They're not actually the same states, okay? But I act the translation on this guy, right? And you can see that this new state, right, after I do this gauge transformation, has a different momentum, right? Which is given by this expression here, right? And so, in other words, this new momentum is the original momentum shifted by 2 pi times mu, where mu is just the charge filling fraction of this lattice. So at the end of the day, you notice that basically this process of inserting a flux and then comparing apples to apples, restoring the original gauge, preserves the many-body momentum when the charge filling is an integer. Okay. But it does not preserve the many-body momentum if the charge filling is fractional. Okay. And then the argument goes, right? So again, the argument goes, look, I've done this very slowly. I've inserted a tiny amount of energy. If the system is gapped, then I must be still in a ground state. Okay, but I can't have the same state with 2 different momenta, right? So I've generated a different momentum if the charge filling is fractional. So basically, either the system must be gapless, or I have to have multiple ground states with different momentum, basically. Okay, meaning that I've spontaneously broken the charge symmetry. Yes.
Yeah, it may be possible that you have a different operator, which is not the Oshikawa operator, but it is also gapless, also gives you a gapless. Is that possible?
Yeah, good. So I think the question is could I have had a different operator that's just a product of a bunch of local, a bunch of single site unitary phase rotations or something like that, that would also, for example, change the many-body momentum and provide such an instruction? And the answer is yes. So in fact, and I'll come to this later. So, the way that this was originally phrased, it was really sort of thinking about this electromagnetic response to flux insertion. But there's a more recent paper, and I'll show you in a minute, that basically says, look, any operator that is just, can be expressed in particular as a product of single site unitaries, among others. Okay, the general thing is like finite depth unitary circuit. If that operator can change the momentum then basically either you've killed translation invariant, you know, either these ground states aren't translation invariant, or they must be gaps. So yes, this is the general. Yeah. Great. Okay. So this is the result for charge filling. And you know, if you think about it, it's very, very intuitive, right? So if the charge filling is integer and I don't have to worry about spin, obviously I can put some integer number of charges on each site. This preserves translation invariance, and you know, it can be gapped, right? This can have a Mott gap, and it can be completely boring, right? So we know of states that look like this, okay? But on the other hand, you know, what's maybe less, when you start looking at, well, you know, maybe I have like one charge for three unit cells, right? And then it's sort of, you know, you can sort of see that it's a little harder to write down states like, you know, that don't break translation invariance and don't break any other symmetries and are gap. It's maybe not so obvious that you cannot do it. So this theorem tells you that, you know, if you have like a fractional filling, either you could break translation invariance and do something like this, or the system actually is going to be gapped. So this is a nice kind of no-go result. Good. Okay. So so what I want to talk about a little bit today is, again, this issue of, you know, let's go beyond charge conservation symmetry and think about actually a system with conserved dipole moment. Okay, so let me start by telling you what I mean by that. So this is a very simple thing. So we're used to thinking about, you know, models where I have electrons. Okay, I have some tight binding model, whatever. You know, these particles can hop. I have some kind of excitation, and it can hop from site to site. And in this situation, right, since the particles are not created or destroyed, I have some total charge which is conserved. But you know, because these particles are moving, the total dipole moment obviously is not conserved. Because you know, I can have one particle and it can change its position. Okay. So what does it mean to have a conserved dipole moment? Well, this happens in systems where you have no single particle hopping, right? I'm going to talk about how you might arrange for that in a minute. But you actually have, you know, correlated hopping, which says, well, this guy can only go this way, this guy can only go right, if this other guy can go left. Okay. And so in this case, you know, again, these kinds of correlated hopping processes certainly conserve the overall charge. So it's the scenario that I'm going to be thinking about. But now they also conserve the dipole moment. Why? Because this particle, you know, this charge has moved one to the right. So its RJ has increased by one, but this other guy has moved one to the left. So its RJ has decreased. So this is the kind of model that you would look at to do that. How many on time, actually?
You have another 15 minutes,
Okay, including questions.
including questions.
All right, that is good. Okay. And so why, you know, like, pretty hard to arrange for this in the material. Why might we think about this? Why might it be interesting? Well, dipole symmetry, you know, was first, at least I first encountered it when people were thinking about sort of fractional quantum Hall effects, which is more material than we now back in the limelight. Okay, fractional quantum Hall effects, and they were trying to understand the structure of, you know, certain fractional quantum Hall wave functions. And one of the things that people did is they said, well, let's imagine I take my 2D quantum Hall system, you know, apply periodic boundary conditions, put it on a torus, and make that torus rather thin. Okay. And it turns out that in this limit, you know, if you take the Coulomb interaction, the lowest Landau level, what it does is actually produce systems with dipole symmetry. And this is actually kind of related to the magnetic translation algebra. And I can talk more about that after the talk to anyone who's interested. So this is one context that, you know, people are sort of trying to understand the lowest Landau level, and you naturally arrive at these models that just have this property that they conserve dipole symmetry. More recently, though, people working on cold atomic gases have started to look at systems with basically tilted, you know, so think of these as charged particles. Really, typically the experiments are with neutral atoms, but you know, imagine that these are sort of charged particles, and its hill is representing a background kind of electric potential. Okay, and so and these wiggles are a lattice. Okay, so you have, you know, particles, atoms, and they're gonna sit at the minima of this optical lattice, okay? But they're also in this background potential. Now, cold atom experiments are always, essentially out of equilibrium, so yes, if you wait for long enough, all of your particles are gonna roll to the bottom of the hill, and you're gonna have, like, your experiment is gonna fall apart, but actually on, experimentally relevant timescales, the energy in these systems is approximately conserved, and what that means is that this atom, well, it is not surprising that it can't jump up the hill, but it also can't just roll down the hill by itself. Why? Because, it has no way to release that energy into the environment on, again, experimentally relevant timescales. And so instead, the dominant dynamics in these experiments, and this is, apparently this idea was, I think, first actually proposed by Alan Morningstar when he was David Hughes' grad student, and then the experiments were done. Okay, but the dominant, dynamics in this system comes from processes where one atom goes up in energy and the other goes down in energy, so that energy is conserved. Okay, so we now have a new class of experimental systems that can realize, at least, approximately long wavelengths, these dipole symmetries, dipole conservation, dipole. Okay. And so dipole conservation is kind of interesting because it's a lot like charge conservation in some ways, but it's also fundamentally different in rather important ways. Okay, so the first observation is that you can ask, like, is the dipole moment itself ever really conserved? And if I think of a 1D line that extends from -infinity to infinity, and I have correlated hopping, the answer is yes, the dipole moment is absolutely conserved. Okay. But if I then take my system and I say, well, look, I'm actually, I get to work with finite numbers of sites, makes my life easier. I can study them numerically. I'm going to put this on periodic boundary conditions. Okay. And now actually the dipole moment kind of can't be exactly conserved. Why? Because I move one charge around the system. Again, let's imagine that I keep everything else fixed. I move this guy once around the system. Well, its position has now changed by L, and therefore the dipole moment can only possibly be conserved modulo L. Okay. So basically, because the dipole symmetry talks to spatial symmetry, it talks to translation invariance, it is sensitive to things like the spatial boundary conditions, and in particular, in the scenario that I'm going to think about, where we're working with periodic boundary conditions, it is never a continuous symmetry. It is always discrete. The dipole moment can only be conserved modulo L. Okay. This also means that fill in 0 and fill in 1 are the same. Okay, good. And so in particular, when we look at the actual symmetry, so the phase rotations generated by this dipole charge operator, these phase rotations are now just so the associated symmetries. Good. Now, oh yeah, and so now let me make a comment. So the first kind of interesting thing that you observe when you start thinking about dipole symmetry, and this is, I think, particularly relevant for the story of sort of things about fractional quantum states, right? Is you can ask, let's go back to this argument about fractional charge filling in one dimension. And an observation is that actually this gauge transformation operator that we used to make this argument is none other than the dipole symmetry operator. Okay, and so when you have both charge conservation, translation invariance, dipole conservation, and fractional charge, as you do in these thin fluorescent all systems, you are guaranteed to have an exact ground state degeneracy because now this is a symmetry. So these two states are going to have the same.
10 minutes.
Thanks. Okay. And so this is kind of a cute observation that you can make. But the question that we were most interested in, particularly as people start to try to understand the phase diagrams of these tilted lattice systems, is suppose that I'm at integer charge. Okay, so if I didn't have dipole conservation, then there'd be no obstructions, making one of these very boring gaps and then blah 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 ground states. Okay. But now I also have this dipole filling fraction. I might like to know, can I make a boring ground state for any dipole filling fraction, or are there obstructions to doing that similar to the way there are obstructions for charge? Okay. And so now, we're gonna come back to this kind of more general form of the argument. There is a subtlety about, a second subtlety about dipole symmetry. And another way that it's different from, kind of V1 symmetry is if you imagine, so let's imagine that I put a flux through my system, and instead of hopping a single charge around, I can only hop a dipole around, okay? And so now basically, so the blue is one charge, the red is another charge. And so now basically, the net phase of the wave function due to this magnetic flux is 0 because the Aharonov-Bohm phase due to the positive charge and the Aharonov-Bohm phase due to the negative charge exactly cancel each other. Okay. And so, if you wanted to get a non-trivial Aharonov-Bohm phase, you'd actually have to have a winding, not of the gauge field itself, but of its derivative, which typically, we don't allow. Okay. Usually require this to vanish. You can introduce a sort of fictitious analog of the electromagnetic field, though, that allows this kind of winding. You can think about these things, but partly because of this, it's useful to sort of realize that we don't actually need to do flux insertion to do Masaki Ushikawa's argument. In fact, all we need is this sort of local unitary operator. And so again, this result, and I'm not going to kind of go into the details of where it comes from, but this comes from a paper due to Gaioya and Wang, and they basically show that if you have a system with translation invariance, and so this is a picture of sort of applying unitary operators in layers, okay? And then you have some finite, layers of, unitaries here. They're each acting on two sites. But maybe in our case, they're acting on a single site, okay? But, whatever this is, you have, you act with a few kind of layers of unitaries, and you produce a state with a different momentum, okay? That basically that means that this ground state could not be symmetric, like it can't be translation symmetric, and gapped and non-degenerate at the same time. So this rules out boring ground states. Just the fact that I had this operator here that shifted the many body momentum, and this was like this simple operator, just applying some phase rotation to each site that depends on the charge. Okay. So there is a similar operator in dipole conserving systems. And it looks like this, okay? So again, you can think of this as a sort of large gauge transformation if I introduce this kind of more general gauge field that would allow for flux for the dipoles. But the important thing is that it is simply it's a product over the whole system of just a position-dependent phase rotation on each site, okay? This is an operator that does change the total momentum, again, under certain circumstances, because due to this position dependence, it doesn't commute with translation. And so how does it change the total momentum? Well, it changes the total momentum by, and again, changes this crystal momentum, so it changes by 2 pi a don't count, okay? So it changes the total momentum only if this quantity here, so mu d is the dipole filling, the total dipole charge divided by the system size, and u is the charge filling, okay? And the momentum is conserved by this local by this operator O only when this is an even integer. Okay. So this is the criterion. I think it's gratifying to check that this criterion makes sense in the following way. So imagine that I have a system where on each site I just put some charge Q, so the charge filling of this would be Q, okay? Again, clearly I've filled every site. This certainly qualifies as a boring ground state when there's no spin or extra degrees of freedom in here. Okay, the dipole filling now you can calculate as just mu L plus 1/2, okay? And so you can see that the dipole filling for this is going to be an integer, either if L is odd or if L is even and Q is also even. And it's going to be a half integer if Q is odd but L is even. Okay. Thanks. I will be done. Okay. And so this is exactly the context in which our our sort of predictor predicts that these ground states are can be boring. Okay, so certainly when this momentum doesn't change, we can write down explicitly these boring ground states that are compatible with both the charge filling and the dipole filling. Okay. And then we can rule out that we can have boring, gapped symmetric ground states and other fillings. You can actually verify this numerically. So these are some numerics that Sanjay did. This is a model. So this is a spin 1 model, okay, in which here the charge is the spin in the z direction, okay, and it conserves both charge and dipole moment in SZ, okay. And you can see that, so here's a Hamiltonian we looked at, and you can see that we have these nice gaps when we have dipole filling 0 or 1, and 1 is equivalent to 0. And then at all other fillings, the system appears to be gapless to the best of our ability to resolve the pair. Okay. So that's the basic message, right? These Lieb-Schultz-Mattis type theorems are powerful ways of sort of understanding when you have to have some kind of non-trivial physics, right? It's not just some boring, or mod insulator, ferrite, whatever. And there is an analog of these arguments for these more generalized symmetries associated specifically with dipole moment conservation. And in particular, for a given system size and charge filling, there's only there's only one choice. Once I fix the L and the charge filling, sorry, I don't know where this 2 came from. There's only one choice of dipole filling that is actually compatible with that, and all of these other states are either gapless or symmetric. So let me end there. And
Great, thank you. Please, Karen.
Thank you, Fiona, for a nice talk. Could your arguments be generalized to higher multipoles like quadrupolar?
Yeah.
Or octopolar?
Yeah, I think so. And I expect, so actually, we haven't done that explicitly, but I expect that it would sort of generalize in the obvious way. So, basically, as the dipole moment is is associated with the gauge transformation for the charge, okay, and then this object, which is the gauge transformation for dipole, would be the charge of like a quadrupole. So that kind of goes like J squared. So yes, I think that's true. I don't know of like physically motivated examples where microscopically those higher movements are conserved, which I think is why they haven't got as much attention. But yeah, but certainly they're relevant in band topology. Of course, yeah.
Okay, thank you.
I have a question about n even versus n on.
Yeah.
I mean, is there something, maybe you talked about it and I missed it, but it feels that there should be something different.
About like even and odd systems.
Yes.
Yeah, that's right. So and they're different, but they're so the criterion is different, but it's different in a sort of trivial way. And that's because if you calculate, so you just take our system, maybe this is busy, right? We just take our system with this charge Q on each site, okay? Yeah. And you calculate the dipole moment, right? And so that dipole moment turns out to be this little q times L plus 1/2. So the dipole filling is that number divided by L, right? So the dipole filling is this little q, which is also the charge filling, times L plus 1/2, right? And so now you see that if mu or q is odd and L is even, then this has to be a half integer in order for or like if you have a state like this, this is a half. So this is where the half integer dipole filling versus integer dipole filling these gaps.
So I mean, can you also then allow yourself to think about something which actually has like ferroelectric?
Maybe can you say a bit more about?
Well, I mean, suppose I had a half-foot system. Then I probably need an extra label on this, but of course, the standard thing is they go plus minus, plus minus, plus minus, plus minus.
Yeah.
Even number, when I end up with a big dipole pointing that way.
Oh, yes.
If I take that charge to the other end, I end up with a big dipole pointing the other way, which is nonetheless macroscopic. So
yeah. So Yes, good. So that would be, that state would be an example of, like, I would call that non-trivial, because since you have this plus minus plus minus plus minus,
Yeah.
you have, okay, so you have two choices. Either you started microscopically with a two-site unit cell,
Yeah.
right?
Yeah.
But then you would be in this case of having, one charge per unit cell, okay? Or you have broken the translations. So if you, so that's the way, so in other words, it need not be that exotic, you might just break the translation and have it stuff.
Okay, so I see, so that comes in broken translation symmetry, but in the end, there's a dipole label on that. Which
Yeah,
is
yeah,
associated
it's still,
with.
that's right, it would still have a dipole moment, yeah, absolutely, yeah.
Yes.
So I have a comment. I mean, first place, sort of disagree with the definition of boring, but what you've discussed are actually not necessary conditions for interesting, but I mean, not.
That's right.
So you can, I could take your interesting ground state and change the Hamiltonian, make there be 2 atoms per unit cell, and it's still interesting in that it still has the same topological order.
Yes.
Or we could take a quantum Hall system and put a little bit of periodic potential, so dipoles no longer conserved, but still have the fraction quantum Hall effect.
Yes, yeah, absolutely. So I think, yeah, good. So the relevant part of this is that, what it says is, under certain conditions, you can't just have this kind of like, you can't just have, this, a charge, whatever, 1 or 2, 3, it's all like mod insulator, it's, but certainly the fact that I have 1 particle per unit cell does not necessarily mean that I'm doing something, that this is the state. I guess certainly like when I think about like spin liquids, right? I mean, kind of like often in nature, when you can do something boring, that turns out to be very stable. And so like usually, these are good criteria to have in mind when you're looking for something. But yes, it need not be so.
Well, thank you very much. That was good. We will come back at 10:40. 10:40.
Oh, good, okay, yeah, I.
Well, as I say, it's the
Yeah, I mean, these days, those, I mean,
Sure, that's the reason I.
that's Ditelluride or something.
Yes, yes. Oh, okay.
Let's see.
Terrific.
Yeah, it's a bit.
Yeah, we didn't do it. Simple, things just didn't record. Yes. Yes. Yes, you're looking for.
We're looking for the splitting.
Yes, it's.
That's quite hard to resolve.
I think it would be interesting.
I think the higher dopings, there, the field.
You have to go, I see, so it's hard to resolve this.
Yeah, we actually tried the high field experiments. Otherwise, we would have seen.
Yeah, then you probably would have, I see what you're saying. Okay, so in that sense, in obviously.
I'm after lunch.
I mean,
That's, but I think as it is. So what you good, so we did the session, we have a research. In uranium, Ditelluride.
All right, well, I'd like to start, thanking you for my invitation. It's my pleasure to talk to you about, yes, magnetic excitation. So there's a lot of stuff that I could actually talk to you about, regarding uranium Ditelluride. So this is the scattering workshop of sorts, so that's sort of the focus. Before I start, I want to acknowledge that I don't really do a lot of the work. It's mostly my group, so postdocs Corey, Sylvia, Peter, and Tom, who's in fact there actually is responsible for a lot of the neutron scattering, and of course Shane, who's the postdoc now in University of St. Louis, started this form better. I also want to point out that this is, even though our reactor is shut down, we do still accept applicants to the Emerson postdoc program. If you are a U.S. citizen, you might be interested in doing that. Please talk to me afterward. Okay, so this is what I'm going to talk about today in our half hour. So I'll introduce just and I'll also preface this. So I'm happy. Okay, also I'm happy to take questions in the middle. So if there's something that you don't like or don't understand, please just raise your hand. I'm going to just give you a very brief overview of why we claim that there's unconventional superconductivity in this material. I will highlight some of what I think are very exciting recent results on high field superconductivity. And then I'm going to spend about half the talk talking about what we think we understand about magnetic interactions in the material and what neutron scattering tells us. So to begin with, yes, it's a superconductor. Saw that in the title. Resistance goes to 0. In the original data, it was about 1.6 Kelvin. Now we know that TC and the newest samples, we can get it up to about 2.6. Okay. But that by itself is not an exciting thing. Everybody's involved in superconductors. So what's so exciting? Well, we knew almost from the get-go that something weird was going on when we were trying to map out the critical field curves for UT2. And so this is an orthorhombic system, and so we were just looking along the three main crystallographic directions. The A-axis here looks fairly conventionally, but 6 times looks pretty big. And by the way, so this is from the first, generation of samples of 1.6 going into C. These are already fairly large. C-axis is here, B-axis is here, and this is literally what happened. So when we first did the measurements, we thought maybe the magnet was broken. And 20 Tesla is about as big as we could go at the university. We know now that it's 35. And it's actually not even a simple story because here's the data set from Mag Lab in Tallahassee. Nice zero resistance all the way up to almost 35 Tesla. You see electrons up. But that actually coincides with the step in the magnetism. And so two things to take home from here. One is that the polyparamagnetic limit is exceeded in all directions. That's a reason already to believe that we do not have a spin singlet state. That is, the spins in the Cooper pairs are parallel, or we would have expected them to have already dispersed. The other thing is that, at least along certain special directions, the superconductivity could actually even extend further up. And in the next couple of slides, we'll touch back on that in a little bit. So if we have a spin triplet pairing state, then we would expect to have some kind of odd parity in the equivalent. So we have, I suppose I always say, we build a circumstantial case typically for this kind of stuff. Evidence starting from the earliest days from the heat capacities, non-exponential measurements of the penetration depth up to these recent ones suggest that there are point modes. NMR is a little bit of a more complicated story now. From the get-go, it was clear that there was a very small night shift through the transition temperature. As time has gone on, and most recently, there has been a claim that night shift is larger, but not necessarily, it's not actually not clear from here that it's a full gap, but the story is maybe in the newer generation of samples, it's noted. I'm not gonna give you an explanation for why, because I don't actually quite understand the argument, and I say I don't really agree with it, but in a similar vein, at least thematically, what's happening is that thermal conductivity expression. So what I'm showing you here, just to give you again a sense of what thermal conductivity says, is the zero temperature limit of the thermal conductivity as a function. And so then what one typically does is compare what we've measured in your material versus what we know from, let's say, S-wave superconductors or some other unconventional ones, and then say, oh, this is simple. So from the earliest days, it seemed like UT2 was not really an S-wave system. Then more recently, Matsuda's group published results that said, hey, actually it looks more like niobium. And then this is work from JP's with the UMD, again, saying, well, actually, if we compare samples with different scattering, so, and this is normalized HT2, so this is different TCs, of course, that it actually still looks like there are nodes. Now, not only, I suppose, if I wanted to be agnostic and take a step back and say, okay, so there's some disagreement now. The crux of the matter still, to my mind, is that it's hard to understand how, with higher TC samples, less scattering, less disorder, one would have you would be moving towards a nodeless sort of orbital character. And sorry, but all the data then in panels 2 and 3 in the middle and to the right on these newer generation of samples, or? Okay. So are you asking about these guys? So this is a comparison only of quote unquote generation samples to UPT3 and niobium. So that's from the Matsuda group. Here is a comparison of only UT2 of different TCs or different scattering. So ranging from the original to the yeah, essentially.
Yes, is there an ordering which ones have the highest TCs?
So the ones that have the highest TCs are so samples 3. Okay. So it looks like it dips down, right? But there's always the low fields.
But isn't there a theorem that residual kappa over T should not depend on disorder, on scattering?
No, but
there is a theorem that that kappa of T.
That's in 2 dimensions.
Huh?
That's in 2 dimensions.
Only 2
oh,
dimensions.
that's right. In 2D, there is a universal.
But the physics is the same, right? I mean, there's a spot is getting bigger and the number of.
I'm happy to talk about this later, so that's all. So, I apologize simply because I want to get to it. So anyways, just to leave you with sort of an idea of what the discussion is really. So, what I'd like to first focus on, as I said, is a short highlight of some new high field results we have. So in order to sort of introduce you to that, this is not a simple phase diagram. This is a zero temperature phase diagram. So what we're looking at here is magnetic field value and then tilting from the B-axis. Remember, I told you that there's a superconducting, that there's superconductivity that there persists to 35 Tesla. This is sort of the envelope of the low field part, which isn't really that low. And then above here is what we're calling a field polarized phase on the other side of the metamagnetic transition. This thing here is another pocket of superconductivity that we find when we tilt the magnetic field between the B-axis and the C-axis. It's a purely reentrant phase, and it only exists on the upper field side of the metamagnetic phase tree. It was dubbed Lazarus by clever people at the press office of the MagLab. You go ahead. So for those who don't get the biblical reference, this is brought back to life. Okay. So and I find it out. Okay. So we know a bit more about the this behavior, or let's see, the superconductivity since those early days. First thing is I want to emphasize is we're looking at SC2, or this thing called, so here SCRE along the B-axis. Here's actually the temperature dependence of this. And it actually is sample dependent, but one could argue that, in the higher, these aren't even, and these are from early measurements. So this might also be due to angle misalignment. But at the end of the day, what it looks like is that this phase is reentrant in some sense, so it kind of pushes in like this. We know now from more recent experiments that there actually is a heat capacity anomaly, and that it is likely a separate superconducting phase. All right. Now, if we look at a similar temperature field dependence of the upper part, so this pocket, so if I'm going along the slice here, Then, the thing to note from this plot is there's only two data sets, because these aren't easy experiments to do. The TC is roughly comparable to the low field. And so what I'd like to point out to everybody all the time is that if one just takes the temperature field phase diagrams, which is HT2 curves, and plots them comparing with the cuprates and the nictides, this is a delta. Okay. That's pretty remarkable. So if you take nothing else away from this talk, just understand that UT2 is really weird and it fundamentally is interesting because it's that big. So before I get to the magnetic interactions, I want to talk about two recent experiment or two recent, let's say, conclusions that are things that we have to say coming about this Lazarus. So the first thing is this orphan business. So in all our theories of high field superconductivity, there's always an assumption that there is a zero field superconductor phase that's stable, with perhaps some exception, but this is the expectation. It turns out, not surprisingly, that if you change the amount of disorder in the samples, that you can suppress superconductivity. But what is surprising is that you can suppress the low field superconductivity while still maintaining some high field superconductivity. So the word orphan comes from the fact that you kill the parent phase, but you still have a child. Okay, what we're showing here is how the angular extent of that orphan phase is smaller, but it's still there. Now, looking at the temperature dependence of it, of course, it's also weaker, but it's still clearly there. So, as I said, we have to talk about what is actually responsible for stabilizing high field superconductivity. And now, highlight two, and this is more recent work, is we managed to map out the angle dependence. So this is what I showed you in the beginning. There's a pocket here, right? Turns out it's not really a pocket. It's really a halo. So if we are, so what I'd like to do, what you to do in your mind is, so these actually were orthogonal, right? Going towards A and C. So this is how I would plot it here. If you're able to tilt now in the perpendicular direction, you see that superconductivity actually exists out sideways. Now, I don't have an explanation for you, okay? But it's patently weird, and there are obviously, this has to be clues in this about like what's actually the underlying mechanism. We don't really quite understand. So there you go. So any questions?
Well, Nick, I have lots of questions, but I wanted to ask the disorder that leads to your that suppresses the low temperature the low field superconductivity. Is it just garden variety disorder? Is it magnetic disorder? What kind of?
That's an excellent question. So the first thing I will say is it's not, it wasn't due to intentional substitution of any kind. Therefore, I cannot tell you whether it's, whether it's magnetic in nature or not. We don't fundamentally understand what defects are responsible for stabilizing or destabilizing superconductivity, I suppose. So when we have higher, or what's leading to less scattering, and whether those are the same thing. In other words, those triple R really and triple R and TC really like, you know, one-to-one correspondence.
What kind of magnetic resistance do we have here? Suppose that you are in the normal state at low temperature. Would you have considerable effect of magnetic field on the resistivity?
Yes, it does change. I'm going to say a factor of 2, maybe.
Smaller?
It's not that big, yeah. So these aren't like.
This is the range where you see this dip in the whole number, right?
If you're referring to the other experiments, that's in the high field side.
High field.
Yeah, that's.
No, but I mean, in the field where your saddle appears.
Yeah.
What happened?
What's happening with
Anything happened
resistance?
there with the resistivity?
Okay, the resistance always increases in this metamagnetic state. As a function of angle, we do not have resistance measurements at every angle. So I can't tell you in detail what's going on with the M1. Okay. That is a thing that we could do. I will say one of the features of this experiment is it's mostly the superconductivity is delineated by measurements of diode oscillator frequency, which is a contactless conductance experiment, and so I can't directly answer that question. And that's for technical, which are, it's really hard to measure resistance of small samples in high magnetic fields without things breaking. All right. So I'm sorry if that wasn't definitive, but there's a lot we still don't know. Having said that, I want to take you back to talking about magnetism. And the reason is we do have materials that have been around for a while that look similar. I don't want to say superficially similar. There's something very compelling about seeing enrichment superconductivity in another class of uranium compounds, rhodium, germanium, and cobalt germanium, which are actually ferromagnetic. And you know, it's believed that this business here with reentrance is related to spin reorientation or something like that, having to do with breaking the ferromagnetic state. So let's talk about what we know about uranium ditelluride, both in terms of magnetism and the electronic state, the conduction. First is that this is what the resistivity as a function of temperature looks like along different directions. It's a negative slope, so I would say, okay, it's it's a heavy fermion compound. It looks like many heavy fermion compounds. And the other thing is that it's not very anisotropic in terms of the total scatter. Magnetic susceptibility looks like this. There's a peak in the B-axis magnetization, but the A-axis susceptibility is the strongest. That doesn't order. Here's the field dependency of the temperature. If I were to just qualify it as a heavy fermion compound, the ratio of the specific heat to the susceptibility is about conventional. We also looked in the beginning for any signs of ferromagnetism at low temperatures and say that the order moment in the bulk magnetometry has to be really, really small. And there haven't been any reports of magnetic transitions along range order in any experiments since. So we're dealing with the paramagnet. How about its electronic structure? So I'm showing you here first a hypothetical compound thorium 2, and just these kind of 2D Fermi sheets. It doesn't exist in nature, but this is what you would get without F electrons. So that's the reason to have it. Okay. Once we throw F electrons in, your imagination is the limit, because pretty much first principles calculations have been able to come up with like whatever shape you want. Being slightly facetious, but there's a lot of wiggle. The Hosfin Alpin experiments are sensitive to, or basically have detected, Fermi surface that looks like this with some modulation. So that's the story. ARPES, which I haven't really seen any results actually in the last couple of years, have shown basically in agreement with the bands that give rise to this, but don't have the resolution to tell us what is going on in detail at low energies. And one of the consequences of this inability to say for sure what's going on is an argument going on right now about whether there is a three-dimensional pocket based off of suggestions both from ARPES and from the Hosfin Alpin. So that's where we are. So if we have only a 2D Fermi surface, you have to ask why is the transport quite isotropic, and why also when we have what we expect, well, we know it's a renormalized Fermi surface that is interaction with the up electrons. Why does the area, cross-sectional area, still look the same? So
Are the quantum oscillations also seen in the low TC samples?
no, there is a threshold in terms of scattering, right? In terms of which, so and I don't know that number. I don't know that that's a part of it. I guess I'll say that, but you don't have to be in the highest TC sample. So once you get to about 1.8 kelvins. And I sort of said that there is no one-to-one relation between RRR and TC. There is definitely a relationship, but there is actually quite a lot of scatter. So, okay, so other reasons then to, you know, go back to magnetism, to compare to the uranium, cobalt, germanium, uranium, rhodium, germanium, even uranium, germanium 2 are this motif of uranium tellurium atoms, this kind of zigzag trees. And so that left us to saying at the beginning, maybe UT2 is the end member of a series of ferromagnetic superconductors. Okay, why would we be interested in selling it? Well, ferromagnetic superconductors tend to be topologically non-trivial, and if we're worried about qubits and the like, this would is another attractive thing. So what do we know beyond bulk magnetometry? And we're gonna get to neutron scattering first. Well, there have been USR experiments, optical curve rotation and scanning split experiments, so just lumping them all on the same page. Similar, I guess, theme to the uncertainty or argument about nodal nature of the superconductivity is that there isn't really, there have been some sort of changes in the story as time has gone on. And so from USR, for example, we started off with arguments that the material looks like it's close to ferromagnetic instability, to possibly or likely that there is magnetic short range order that's due to presumably defects. But then in the most recent experiments, there are no magnetic clusters of short range order. Optical curve experiments have suggested proximity to ferromagnetism, and scanning squid experiments from Stanford have shown that there's a possible term. So we're sort of from these experiments, maybe we don't have any hard evidence one way or the other. And it is a question of what is the correlation between any of these statements and the amount of disorder. How about neutron scattering? Well, there was a lot of excitement from the initial neutron scattering experiments that were published. From Hung-Cheng Dai's group, there was a clear indication of excitations at non-zero momentum transfer, and no signatures of ferromagnetic light scattering, so nothing near the brightness. This was should I say? This was confirmed by French group, and the thing that caused excitement here was that, you know, as opposed to our expectation that this is going to be like uranium, germanium-2, uranium, cobalt, etc., there is clear evidence for that. Rather, the statement that there are excitations at decommensurate wave vectors suggests that there are antiferromagnetic correlations, but there is no antiferromagnetic order. There's no long range order. So where does this stuff come from? And that's what I'm going to spend the rest of the talk talking about.
You have 14 minutes. Okay, including questions.
Yeah, good. So I'm going to talk to you first to give you the background on some experiments that we did at the Center for Neutron Research. I like to always show pictures of the samples because these crystals don't grow larger than, well, I'm sorry, we can get large crystals, but they're not single. Large crystals, which are not single crystals, they are twinned and things like that. So the experiments that I'm going to talk to you about inevitably require co-aligning lots of samples, and this requires lots of time. So let's give credit to the students who are in postdocs who had to go through the labor of doing this. But here we go. I'm showing you here maps at constant energy transfer of in the AB plane. Okay. So A, recall, is the strongest susceptibility, we call it the z-axis, and the B direction is the one that actually where the susceptibility undergoes a maximum. And it turns out that all of the scattering exists at along the B direction and lives at the edges of the Burnell. So I hope you can see the red overlay. You'll notice that it's these are octagons and rectangles, and the reason for that is because this is a slice of the body-centered orthorhombic cell. And so, you know, using this basis, we're cutting across the top of the neighboring Brillouin zone, etc. So blue and red are dissimilar, are not symmetrically equivalent. And so actually these things do not fall halfway in between. They fall at not random, but you know, geometrically determined point. Or number. So this is the thing. So and you can also just tell as you compare different energies that it's kind of brightest around 3 to 4 meters. So let's look at it. So if I take if I ask what is the I want to like now say the energy versus momentum, that's the dispersion along the green line. So going here perpendicular to this thing and then along this. As I go along the green line, I am going from this Brillouin zone to the top, to this Brillouin zone, etc. You'll see these pockets, these things like this.
And these are just slices at constant momentum transfer, so constant Q cuts, and you'll see that this is the line shape. So it looks like this. And this is sort of a summary here of what the peak position is. So this is the dispersion along this direction. And if I look perpendicular to that, you'll see it looks largely flat. That is mostly dispersion. And so this is just another map to show here. So this kind of behavior is not typical of paramagnetic excitations. First of all, there is a gap down here. And as I said, this isn't above a reciprocal lattice point or anything like that. There is no long way source. If we take these excitations and want to talk about the temperature dependence of them, for simplicity, I'm just showing them integrated over this whole thing. You'll see that at 0.2 Kelvin, that is actually even measured in the superconducting state, that there is a lot of intensity here. It's peak about this energy transfer. And as you heat the sample, basically this just kind of washes, right?
You have 10 minutes.
Thanks. This number, 4 MeV, is the same energy as the hybridization gap that we did first on scanning microscopy. And this temperature is the same temperature below. So remember also the magnetic susceptibility undergoes a peak around 40 Kelvin. Optical conductivity, there is development of strong Buddha peak below 40 Kelvin. So when I talk about heavy fermion physics, to me, this, okay, first of all, it's also consistent, but this is sort of what it's pointing to. Okay. And now I want to kind of start to fold in our new results that Tom, who's sitting in the back, if you want to actually quiz anybody about the details, he's the guy to go to, and we have a poster outside. So first things first, this was actually a really interesting experiment for me because Tom designed this sample holder to hold our samples. And this is actually kind of a cool concept of stacking plates. So I didn't say, in addition to the variation from different synthesis parameters, these crystals are air sensitive. And so if you imagine having to do the co-alignment in air, because we don't really have a device to do it, otherwise we have to think about it. And so this lets us do it in a sort of organized way, do a few of them, stash them in an inert atmosphere, come back, etc. And so we, of course, do everything we can to make sure that the exposure is as short as possible. Now, luckily, they don't just poof. We have many hours to do this. But anyway, so here we were going to measure again in the HKO plane. We went to Kamiya at PSI, which is a wonderful instrument. And we minutes in the superconducting state at zero field and also up to 11 decibel. So we did, so this is what we, all right. And here is a summary of those experiments. So I hope that you still have fresh in your mind what I just showed you from the earlier Max experiments. We're showing you here 2 at constant energy cuts, 2 MeV and 3.5, which is, this is the brightest part. And on the left is 0 and on the right is 11. So why did you do that, right? That's not fair, right? The reason is because you can't tell the difference. So one part of the story is that we were not able to detect any significant change in scattering with an 11 Tesla field along the Z-axis. But you know, the scattering is the same. You can actually resolve a little bit more structure here. And I'm going to spend a little bit of time talking about that with the remaining, what's remaining. I mentioned here that the uranium form that the data are consistent with the uranium form factor. That shouldn't be a surprise, but we at least show that there's an envelope function that's consistent with that spin with an A-axis fluid, largely A-axis. Now, what we saw that is different from what I showed you from the Max data is that when we look along, let's see the blue line here, which I told you was largely flat from Max, it actually turns out that one can see a dispersion. That is, there is a dependence, the energies depends on the momentum transfer. I don't have a lot to tell you in terms of the physics about this. This is an interesting additional fact. Other thing that Tom was able to do was absolutely normalize the scattering and integrate to get a reasonable number for the total spin, which means we think we're seeing most of the, if not all of the magnetic excitations. That isn't something missing in high energy. All right, and what could possibly be the cause of this? So I like to show this 1D, it's actually based on 2D, but our 2D model. But this is a model from Burnell from a long time ago. His main point was that one gets inelastic scattering from interband transitions in heavy fermion and intermediate valence systems that look like antiferromagnetic excitations in the absence of antiferromagnetism. And working, well, we'll say, first of all, based on the MFT calculations from Gabi Outliers group, so this is from his former postdoc Cheng Zhang, which is shown up both in ARPES and in the optics experiments. Our understanding of what we're seeing is that there's asymmetric scattering that's basically this stuff, but of course in 2 dimensions. So that's the story. And with the short time remaining, which is how much?
You have 5.5 minutes.
5.5 minutes. I'm going to approach a topic that makes some people uncomfortable.
Including questions.
Can I ask a
Yeah,
question?
sure.
How many bands do you need in the DMFT calculation? Like what is your model? Is it a 2-band model?
I'll refer you to this paper. I don't know the answer off the top of my head. I will say, and I'm not saying this in my defense, but actually an outstanding thing is that what's important is what's going on here at the spark line at the chemical potential. And the calculations cannot tell us definitively what, how many bands are, like what's going on exactly there. This is a plausibility statement. That is, the model does not disagree with what I just said. No, we've been talking to Gabi about this. He would have shut us down, I think, if there was something wrong. We could talk later about this, but basically, it looks like this thing is actually, could be essentially 2 one-dimensional models, depending on which direction you're going with different energy. So, this thing sitting, the band sitting at different energies with respect to chemical energy. But we can't tell from the calculations, so that's a thing to do. Okay, you may have heard that there were measurements that looking at the temperature dependence of the excitations both in the superconducting and outside of the superconducting state, and that there's a resonance that was observed from Dai's group here, and of course, confirmed by Raymond et al. And so there looks like a little blip at 1 MeV that appears in the superconducting state, but isn't in the. First thing to tell you is from our max experiments, we couldn't confirm it. And the questions that, and I'm not saying from this experiment that we disproved it, I'm just saying we did see it. And then there are questions about why it should be there in the first place. First is why would you see an excitation whose gap or energy is much bigger than the superconducting gap? And why is it sitting at an antiferromagnetic, air quotes, momentum transfer? Chimyasi has an explanation for this. But the thing about the question about the energetics things. So I wanted to first say again that we did measurements originally also in the superconducting state. Can't detect a difference down at low energies. Did notice that the dispersion, that is the momentum energy relationship with the higher energy transfer states, actually still shifts around a bit, even as you pull from 5K down. But so maybe there's still things going on with the band structure at those low temperatures. And then from our community data, now we didn't again do this experiment specifically to look, but it is a fact that with, I would say, better counting statistics, we do not see, we don't see any evidence for this trend, for this resonance. So this is the data from Yuan et al. We would expect to see a bump, and we would expect based on our error. Again, I'm not saying it's not there, we just don't see it. Okay, and so yeah, in conclusion, I hope you remember something about the cool Lazarus stuff in the halo, and I talked to you mostly about magnetic excitation and the Thank you very much.
So the 3 neutron measurements showing the resonance or absence of resonance, I think was your slide 28. Were they all done at samples with comparable TCs of around?
So that's a great
Kelvin,
question. These 2 on the left were definitely, actually, all of them were presumably done with samples around TC of around 1.6. These were done on a mosaic. I want to say this was done on a large scale.
1.6 roughly, but yours has a higher TC, right?
Oh, this one was from the older generation.
Ah,
Kamiya
okay.
data are all from samples with
Yeah.
TC 1.8 or greater.
Right, okay.
So it is actually a statement too, that these excitations, the dominant excitations are not really dependent on sample quality to the extent that we can control, right? So, yes.
Right.
So your speculation that the excitations might arise from interband or intraband transitions, does that explain why you don't see any excitations along the HO direction?
Yeah, and so the phenomenology that I suggest is that we have, it's an allowed transition along K. And for reasons of energetics, wherever the renormalized bands fall, that it is not allowed along H. Yes.
But shouldn't there be a polarization factor involved with this absence of scattering?
There is absolutely a polarization factor involved. The thing is, we would still expect to see the excitations on the edges of symmetrically equivalent ones,
Yes.
you know, right? So they don't show up there.
Is that consistent with the anisotropy and the susceptibility?
Yes, yes, and so I didn't, okay. The B-axis susceptibility is the bulk susceptibility, as I said, undergoes, it experiences a maximum as a function of temperature. And in the other directions, it just kind of, I won't say it diverges, but it's, you know, more period. So, yeah, I mean, to me, again, just from bulk magnetometry, the B-axis already looks special. B-axis is also the direction in which all this stuff happens with the metamagnetic transition and this like sort of finger of superconductivity. So it's probably not accidental, right? But it is perpendicular to the chain direction, the latter.
Well, thank you. I think we should move on. So there was a lot there we could discuss in a real So our next speaker is Maria Gastiasoro. And if I remember rightly, we're going to talk about intertwined order and one to take that stuff.
Okay, so first of all, I'd like to thank the organizers for letting me present his work and, you know, coming back here. I was a postdoc here some years ago. Now I'm back home at the DIPC. The work I'm going to present today is basically, so I'm published, so any feedback is very welcome. So the data was taken at the Kivelson lab, also at the DIPC, and together with the Uranium, we came up with a possible explanation of these domain equations in monolayers techniques. Okay. So the outline of the talk, I'll first present a little bit of this system data, so a brief summary of the system, which I don't believe anyone has talked about yet. I'll talk about chart and segue for the parameters, the variance, and then I'll present a inter-lambda theory, where, you know, basically we find that you need to couple the primary order parameter with a secondary one in order to reproduce the patterns in these domains seen by STM. Okay, and that includes CDW, chart density order parameters, as well as some numeric graph for the parameter that I present. So I'll be showing all this data in monolayer going by the tracking, but before showing the results. So this system has been studied for a long time in bulk form though. And for the purposes of this talk, so all you need to know is that it goes to this chart density with transition at 200K. Was shown already here that the transition was, so there's a softening of the phonon, which is transverse in plane. And you can see here that is mirror odd, right? So there's like think of an accumulation to the left and the depletion charts to the right.
Excuse me,
And
could you try to speak a little louder? It's hard
yes,
to hear.
yes, sorry, yes.
Thank you.
So once this sets in, this is a 2x2 charge density wave. So that means that I'll have the doubling of the unit cell. So this would be my new ordering wave vectors, M1, M2, and M3, related by C3. And the order parameter that I've been talking about has 3 components, each of them associated to these 3 endpoints. Okay. So one slide or one picture about the electronic characteristic of these samples. So this is the DIDV seen by STM. And there is some features as a function of bias voltage. And if you compare to these, there is some undoped electron band structure calculated at the undoped level. And you can certainly identify many of these features. So from the DIDV of STM, it looks like these samples, the monolayer is electron doped all the way up to around here. Yes. And this is not so surprising because it's grown on graphene, so there may be some charge transfer. So this is how the beautiful STM data looks like. This is a topography. So the TC, charge density wave transition, is about 30K higher than above. It's consistent with the few other reports on monolayers. And if you zoom in, you can certainly see that this 2x2 charge order has set in. So you have this doubling of the initial high temperature isolation itself. But something else to notice, I don't know if you can see it already here, it'll be even more obvious later, is that this order survives or is present in nanometer size domains, and there is very rapidly changing features here. I just wanted to highlight that, to mention that these types of domains, charge density waves, have already been reported also in the bulk, but only when you extremely dope the system or you apply pressure and so on. In this case, these are extremely pristine samples. Okay, the monolayer is very, very clean. So another way of looking, or a more clear way, I think, looking at this pattern, so you can either zoom in and look at all the atoms and see, oh, I have some changes in the charge pattern, or I'm showing here some wider field of view. This is again topography now at a larger scale. This is the Fourier transform, so I definitely see in the graphics doubling of the unit cell. So this would be the CD dynamics. In the next slide, it becomes clear why I'm highlighting the next harmonic of the M. So when I take the inverse Fourier transform of the charge density with peaks, that is the yellow peaks here, and I go back to real space, you can certainly see this very obvious domains of this order. Now, it's are kind of one-dimensional. So the ordering wave vector in the system is a particular one, which is the one that is G/2. So the order parameter has to be real. Don't have any phase on, so there is no phase degree of freedom. This was already pointed out a long time ago in these papers. So the Macmillan theory of domain formation, I'll say a few words about this later. When you have a commensurate phase next to an incommensurate phase, you can have this nearly commensurate phase where domains are formed. But the original theory of domain formation was based, needed to phase degree, so we need to somehow modify that. So I saw a very similar theory to create this type of domains where now the amplitude is being modulated, and then you get this kind of thing. commensurate. Commensurate phase domain commensurate. So from here to here, this is just the amplitude of going from 1 to 9.
Sorry, are these single Q?
No, so this is no, it's triple Q.
But then you should have 4 domains, right?
Yes, and you will see them in the
Okay.
things. So this, you cannot tell which 4 domains are those. If you zoom into one of these, you see that its vertex, they have 4. But so that's the first hint. But in order to, exactly, so in order to know what are my domains, I have to extract the data. I have to be careful. So let me show how we did this. So first of all, we have to enforce lattice periodicity. So in these STM experiments, sometimes there is some drag of the second form, which means that even if you are in the symmetric phase, the Fourier transform, and then your bragg peaks are not exactly where they should be, so you can apply a whole transformation to your image so that you have that. And once you have that, so that means that your the phase of the G peaks is constant. You enforce that, and then you can basically write. Let's say I'm going to start with the M part, so the chart with peaks into sines and cosines. Okay, and this is now going to be your order parameter endpoint. So let me just show you how that looks like. If I were to have in real space, if I were to have a uniform or the same amplitude in all 3. Okay, so that's shown here. I have the sine of M, and this is the titanium, selenium up, selenium down. And if I compare with the phonon that is frozen, you can immediately see that the symmetry is definitely, the mirror odd symmetry is not fulfilled at this wave vector. So this is mirror X even, and the same for all the other C3 equivalent directions. So if I take the order parameter information from this peak, it can only represent secondary charges with order parameters. Now, if I go to the next harmonic, now I go to M plus G, okay, like this one here, and I do the same, let's say, theoretical experiment. Let's say, let's assume that now I have a uniform order parameter and the same in all 3 M's, and then I sum this, how would it look like in real space? And now we're talking this. Now this thing is mx odd. So if you look to the left and to the right with respect to the x here, then it has symmetry. So if I want to know anything about the primary order parameter, what I have to extract from the STM data is this one in here. That would be the primary order parameter. And anything that I extract from these order 3, which are odd, even under mirror, then they're going to represent this secondary order parameter, which, by the way, has been reported. So this is some X-ray experiment, recent data where they show that as you go through the transition, so first you have this primary order parameter, which they identify with this phonon, this displacement pattern, this mirror odd, and then you have this other secondary peak raising, which is basically the seleniums above and below going up and down, and that is mirror even, and that is consistent with patterns. So we have these 2 things, and now the next question is what Rafael, I guess, was asking, which is how are these order parameters in these dimensions? Now I know how to extract all this information, so I'm gonna just plot them. So first point, I just go to one of these windows, I apply a lot of Vegeta and I extract all of this. So the first thing we find we did this in several windows, is that delta, so the primary order parameter, and the secondary order parameter follow the same pattern. Okay. The second thing we realized, or the second point to make, is that as you go through these domain patterns, so perpendicular to the domains, these oscillations have clear harmonics. So here I'm showing the three components. So two of them have single Q and 3Q component. That would be the 1 and 3. The pink. They go through this kind of M, W, same thing. And another one has 2Q, the 2Q harmonic. That would be the blue. And I'm showing here, yes, this type of harmonic composition. So in other words, there is a very particular domain pattern these characteristics follow, which is out of all the possibilities. So here you have the 1, 1, 1 we were asking about. They only go through even number of signs. So they go through this A, B, C, A, B, C, A, B, C. They never cross through odd number of signs. Okay, this is another way of plotting this to the dimensions. And then the fourth observation that we realized pretty soon and got us very confused is that if you build some kind of pneumatic vector, so now I'm going to build a two-dimensional object taking the amplitudes of the bractic in the charge density wave phase. So I build this object. In principle, if I'm in the high symmetry phase, this is completely zero because the weights at any of the three bractics, 1, 2, or 3 are the same, so this is zero. Now, in the charge density wave state, this is no longer zero, and it sort of rotates through these domains this way. Okay, so the fourth color, this is the amplitude or the modulus of this vector, and the arrows are the now it's not scalars now and about the direction. And for me, at least, it's a little bit more easy to see this kind of visualization where I go through perpendicular to this domain. So now I'm plotting just one of these charge density wave for the parameters, and the arrows now to these domains are represented by these black arrows. And the first thing that puzzled us was that apparently this new pneumatic order that is there at the bractics when the charge density wave sets in is maximum where these order parameters are minimum. So in this case, it goes to zero. And then in the beginning, it's like, okay, so it couples to the charge density waves. It's not crazy that you would have now some modulations in the charge in the brag sector, but it was puzzling to us in the beginning that it would be. And then when you actually write the allowed couplings, you can hear why it is the case.
Quite a lot, 20 minutes.
Oh, so we're gonna go early plans. Before going through, or instead of going straight away through the details of the Disman-Landau theory, let me just show you the results. So this is the STM data that I just showed, and this is the global minima that is found by this Disman-Landau theory, which is of the type APCP domain pattern. Okay, and so the 2D model can capture both the particular order domain pattern of the experimental order parameters, that would be the 5, delta 1, delta 2, delta 3, and also this pneumatic object of the bracket. And we only find, we looked hard, we played a lot with this model. We only find that this is the global minimum when the secondary order parameter is allowed to be decoupled to the primary order parameter. If not, we never find this. It's never the global minimum. And 2, in many places in the United States, I also need to include the coupling between just like I build a pneumatic and give object for the bracket, I can do so for the charge density wave bigger at M prime. And if these two are coupled, then then I find this. Okay. So how does it work? How does this model work? So first, so I'll just go through 2 points. The first one is why does delta, the primary parameter, have to capital to bind to the secondary one? So if I try to write down the minimum, the simplest possible free energy for the primary order parameter, so that I will have some usual part that give me a homogeneous density way, and then some derivative terms. And why I'm including the derivative terms, which is in momentum space, it would look like a, so in 2D it would look like a Mexican hat. In 1D you have this minimum here, that's not finding Q. And the reason why we are including this, again inspired by this Macmillan theory of many decades ago, where you can have if you have some part in your free energy that likes a commensurate CDW. So here this would be the amplitude, and this is just a CDW that doubles your here, yourself. And then you, for some reason, I don't know, lock the system, you do something to your system, and if there is some other interaction that starts to be important that likes incommensurate CDW, so you take it from M to some small wave vector away from it, and that this would now ignore the lies. So when these two become comparable, there is a region, there's a set of solutions that minimize the energy, but by basically doing these locally commensurate regions, which would be locked to the lattice, and on average would basically satisfy this condition. Okay, so that's what we do for this particular system.
Maria, sorry for a naive question. And how is this different from this Frenkel-Kantorova story?
I don't Oh, yes, that was with the so I'll tell you the story and then you see whether there was a story or not.
Okay, good luck.
You mean the one with Vidya, right?
Hmm?
Yeah.
The Frenkel-Kantorova is just discrete. They often overlap.
But, so I'll tell you the story and then I think that will answer the question.
Okay.
Now that I have motivated why I'm using this type of free energy, then I can ask, how is it that I can get the domain patterns in the experiment with these A, B, C, A, C, P, and immediately one can see that this term, which is shown here for the energetics, if it likes the A, B, C, D, they all have the same energy. This is just 1, 1, 1. So even number of sign. So everyone has the same sign here. 2 of them have the different opposite signs. So then the problem is that to go from A to D, you have to go through a domain where 2 of them are 0. And that's extremely costly for this term. Then we realized, well, if you include the secondary order parameter, because now this secondary order parameter is even under mirror, you can have a cubic term. And the cubic term, I do the same energetics, let's say, analysis, and the cubic term does not mind so much about going from A to B to a state that has 2 zeros. Okay, so that would be so. And in fact, when you install the entire thing, and if anyone is interested in knowing details of how we solve this with harmonics, then you do indeed find that this state is a mean. Okay. And then the second thing that I'd like to highlight or to mention, it's maybe it's obvious for some of you, but something that, as I said, puzzled us was that when going through these domains, the nematic object of the Bragg peak would be peak when the charge using wave order parameter was, the smallest. And then you actually write down the minimum tapping allowed from between the lattice and this starts into weight. So this is the NG that I was showing here. And it can couple only to this type of object. And this object is basically again like some kind of pneumatic ordered parameter of the primary delta. And again, if I have the C3 symmetric, so all delta 1 and delta 2 would be the same, this would be 0. But as I go through these domain boundaries, 2 of them have to go through 0, so 1 of them is left. And in gray here, I'm plotting this N delta. So basically, as I go through the domain, the blue one in this case is left. So my N delta is going to point towards 1. As I go to the second domain, the pink one is now non-zero. The other ones are 0. So my an N delta is going to point towards M3 and so on. So it's always pointing towards M1 and M3, which are the ones that have this single Q and 1 Q and 3 Q components. They are the ones that are remain smaller but non-zero through these domains. And then when you just write this, what does this tell you? This tells you that NG will want to be parallel to this object. So it has to go, in this case, if I choose it to be positive, just anti-parallel, and that's what's seen in the experiment. Okay, so before going to the conclusions, I'd like to spam a little bit or advertise this conference where we're organizing in San Sebastian, September 2 to 6, on quantum phenomena and multi-layers of data structures. There is still spots left. So if you are interested in attending or sending students, postdocs, etc., you can email either of the organizing committee, so Lenny, Paula, Ali, and myself, or yes to this email address. And so with this, I conclude. So some final remarks. So first of all, this is the first time that these domains are reported in monolayer by selenite. It's not clear to us whether they are different from those reported in the bot, because as I said, these are extremely clean samples. So there is no, they just come out, always, no matter what, they are there. We find that the secondary order starts into the ordered parameter matters. So in order to get the experimentally observed patterns of the order starts into the ordered parameters, you need to couple the primary and the secondary one. It could be that in previous STM experiments where the C3 breaking was reported, maybe reconciled with the overlap between these domains. So we certainly always find different windows within the experimental error that these the ordered parameters are this type. Then just in case someone knows the story about the bulk in higher or not. So in this monolayer, this state is certainly higher, but it's right there. And then the final surprise or bad news is that no superconductivity was observed in these samples down to 340 millikelvins. And this is unlike the peak layers, the same system where they show that as this incommensurate phase appears, you have a superconducting dome. So in our case, we serve, and they basically, there's been a bunch of work studying the appearance of these domains to superconductivity. So we definitely have plenty of domains, and unfortunately, no superconductivity. And with that, I'll take questions and.
Yeah, I just trying to understand. So the ground, if you didn't put any gradient term,
yes,
you're saying that your ground state would be the triple Q.
Yeah.
And there are actually 8 domains of the deltas that you can split into 4 groups of domains with the phi's, right?
So I can split them into 8, so
Right.
different twos, and the experimental observation is that 4 of them are.
So, yeah, but one thing that is positive is that these 3Q states, they don't break. They don't break rotational symmetry on their own. But you clearly see, if I look at this domain structure, it almost looks like you're going from an alternation of single Q phases, right? Like the blue, between blue and red. Like, if you look at the nodes, right? What I'm trying to say is that, are you alternating domains of 3Q and single Q?
Yeah, well, so it depends on what you call domain. Right, so this is a cartoon picture, but I would say, yeah, okay, so you have to be a little bit careful. Because when you look at the experiment, this is experimental data. So one thing is when I call the signs and so on. So sure, so this is 3Q, 3Q, 3Q. In order to go from 3Q to this 3Q, 2 of them have to go to 0. Which means that one of them is left, and that you would call 1Q, but I would call that's my, like, I don't know, domain.
Right, but what I'm saying is this, what you're looking at here, this is a modulated phase.
Yes.
But it actually involves all 3 components of your.
Right, but then I
Yes.
would expect to have regions of 0 nematic and then nematic. What I'm confused is that the nematic seems to be also completely modulated.
So here it's 0, right?
But don't you have an extended domain of 3Q? Or you're saying that a perfect 3Q only happens at a point?
Well, in a region, I don't know, here, I would say.
Okay.
I mean, okay, so this is experimental.
What's from the Ginsburg-Landau?
So from the Ginsburg-Landau, I have, right, so I can, yes, so from the Ginsburg-Landau, I guess this is the Ginsburg-Landau, yes. So then I would have.
It's
let's
very
say-
narrow, I see.
Yes, narrow, yes.
Okay.
So this would be the A, B, C, D, and then the time it takes for the. Now, I should say this Ginsburg-Landau only takes a few harmonics, probably with 2 more harmonics, you could find flatter solutions, but
I see.
significantly.
Okay.
But this is just a,
I see, okay.
minimal thing.
It's
with
because you're having
first
first.
harmonic, second, third, up to fifth, including.
Okay.
So I just following up. So sometimes you can think of these modulated phases as really sort of gradually moving the center of symmetry of the CDW from one to the next unit cell to the next unit cell, and it has to find a path to do that.
Right.
The path it's going to choose is basically
Yeah.
what you're determining by the Ginsburg-Landau. But then when you say the nematic order is really associated with the fact that I can think of this as a vector order now, not
Yes.
just as a scalar.
Yes,
So this isn't what I would call flexoelectric, it's rather different.
Right. Right.
right.
This is just, I think,
Yes.
electrostriction.
Yes,
Yeah, yeah.
it's not not electric because, right, because for that you need the U, the displacement, right? So
Yeah.
yes, so it's probably.
Because it's n delta square, right? N
Exactly.
is
Yeah.
strain
Yes,
delta
exactly.
square.
Yeah, so it's not the U.
Good, no,
So
Yeah.
just maybe a quick question. How is the Ginsburg-Landau deformed when you do break C3 by hand? So does any nematicity disappear in each other in a preferred direction? Let's say I have uniaxial strain in the actual system. Would I just choose one direction and that's
So I never like
not good?
played with that, but
But I guess
yes.
the nematicity disappears completely, or is there a?
No, break it if you are putting it by.
I'm putting, yeah, but I'm basically choosing, so how would this look like in terms of the phi's in this case, or?
You put uniaxial.
Yes.
I don't know how it look like. If this was still the ground state, which I don't know, one should check that there is no other ground state that is not first. In terms of, it could be that now the system prefers the delta 0, and the 111 is no longer the ground state. If it's still the ground state, maybe along that particular direction, you would find that certainly one of these components, so the 111 would no longer be the case. So maybe have, I don't know, 1.8 per day, something like that. But
Because I'm just asking if experimentally, I mean, the C3 is well preserved, right? There's no problem with
yes,
that.
yes, so at high temperatures it is, and it's only, this is only appears when you go through the transition substance.
Thank you, that's.
Yes.
So I have a question, maybe best after the image that you first showed.
Yeah.
On the very last slide, so.
So-
No, keep going, the very end. We'll probably use this. Yes. So can I just check, when you're doing the inverse FFT, you're using all of the M peaks to generate that?
Yes.
And if you just do dark field on a single M peak, you find that certain of these light up with certain colors?
So.
Because
So
I
they are
guess I just
actually,
get-
they are readable, they are
I know that.
readable over,
So I
but
guess-
it's not as
I guess what I'm asking is what is happening here?
in the vertex.
At the vertex, right? Is that? Because I mean, I would like to interpret this as you say,
So
there's
the
a
amplitude, that's a point where the amplitude goes
the zero.
down. Yeah.
But you're saying that all of this arrangement is still has this primary modulation vector, which is in that direction, and this is just a.
Yes,
It's just a shift sideways.
every time you go to one of these.
I see. So, but you don't see anything where you get those. There's no delay. Well, then it looks like there might be. a delay.
Yes, no, sure, I mean, so here, right?
Okay.
So what this, okay, so what, this is still an open question on what this model doesn't tell you. Although there is a coupling that you have to take into account, is how does the system choose where the domains, so the direction where these domains develop. But there is a coupling term that.
Just as a quick comment, that this exact same should also appear in these Kagome metals. In that case, it's the L point plays a role over M1 minus, but the Ginsburg-Landau is identical.
I know.
And it'll be, I don't think anyone has seen this particular domain, but it would be nice for people who have done STM, the living crap out of all this. So it may be interesting to see if they find that as well.
I
Well,
think
those are three dimensional.
we get
That is true.
we get to lunch.
Nobody-
This is filled, so it's much easier to.
But if you can add with the IC after the same story.
Yeah.
Okay, I think now, since the discussion did the audience.
So we'll meet again at 1:20.
Yeah.